All right. Here's Lake Superior. Now, we were just looking at a map where we saw that how this lobe came off, and we saw the drain forms, the drainage patterns coming down and then tying into the St. Croix, which you can't really see on here, but it comes in right here. But if we go up to Nipigon, Lake Nipigon, which we've looked at before, but if I go to a closer up, you can see that there's a basin here with I think it's about a 400-foot deep lake. And then you've got all of this evidence of catastrophic outflow to the south. And that water would have flowed right on down this way and contributed to the turbulence we saw. So some of that water, anyway, ultimately was coming from Lake Nipigon. Now, the current models would suggest that the outflow of Lake Nipigon was caused by the inflow from the northwest of Lake Agassiz, which may be yes, maybe no. I think that's something that's worth looking at further. And in fact, I think the whole concept of Lake Agassiz is worth looking at further. Because when you say a lake, you're talking about people get a specific image in their mind, Lake so-and-so. Well, Lake Superior. Okay, if I showed you a map from 50 years ago of Lake Superior, it would pretty much look just like this map, right? I mean, you would instantly recognize, oh, that's Lake Superior. For the most part, any lake you could look at from 20 years, 50 years, 100 years, you're going to see some differences, of course. I mean, let's say that it's a small lake and it gets overgrown and with plants or whatever, and it begins turning into peat. Sometimes you'll see lakes that are shrinking because they're becoming peatified. The peat is moving in and encroaching. I've seen that in lakes that, because there's so many in lakes in Minnesota. I've seen that happen to lakes that I was aware of as a kid. They're shrinking in size because the organic material is actually encroaching and building up layers of peat around the origin. So you might have, my point being is that you might see changes like that, but overall, you're not going to see any real significant difference. In other words, Lake Nipigon, if we went back 100 years ago, these islands that are in Lake Nipigon here, they were there. Now, the water level may fluctuate. Certainly, it may fluctuate, but it fluctuates within fairly limited boundaries. Other lakes, will have more extreme fluctuations, but nonetheless, they're fluctuating about this mean value that doesn't really change a whole lot from decade to decade to decade, right? You get my point. So when you say lake, you're getting this picture in your mind of kind of a static water body. What I'm suggesting is that some of the things that we're calling lakes aren't really lakes. They leave after effects that look a lot like what a lake would do, right? They build up layers of laminated layers. They build up, say, delta type areas where a water, if you have a lake and you have a river flowing into that lake, and that river is charged with sediment, and that river is flowing, and again, as we've talked about repeatedly, the volume of sediment, the amount of sediment, the size of the sediment is all a function of the velocity of the water flow, the current flow, right? So when it's being channelized, it's moving at one velocity. If it opens into a basin, and especially if there's a body of standing water in that basin, what happens? The sediment-laden current flow enters into the basin, slows down, and it begins building a delta. And that delta could be below completely the water, or partially below and partially above, depending on the levels of maximum peak floods, but it's going to build this delta out. And by examining the sediment, and that sediment that's being carried into current, it's coming from somewhere upstream, right? It may come a mile upstream or 100 miles or 500 miles upstream. It's being carried down. But by analyzing the sediment, you can go, oh, okay, this is part of this quartzite sediment whose outcrop is, 100 miles north of here in such and such province or whatever, right? So you can work out the province of the material that is being flushed into the body of water. But here's what I'm getting at. I'm getting at is that, let's say you have this lake, and over centuries, you've got a river flowing into it, building up a delta, right? And in the spring, let's say typically it's going to be heavier rains, more discharge, more sediment, and coarser sediment. Now, let's say we get towards the end of the summer, the amount of rain declines, the water slows down. So the sediment that it's carrying is of a less coarse. So it's coarser in the spring because there's more volume and more velocity. As the volume and the velocity decline later in the summer, the sediment load gets finer. So what happens is you get this couplet, it's called. So it's coarse on the bottom, which represents the spring, and it's finer grained. It's a graded couplet. So it grades up into finer stuff that could be the fall. And then if it's in the northern hemisphere, it may stop altogether for a while because it's winter now and everything is frozen up. Now spring melt comes, you have flushing of water, flushing of sediment into the lakes and so on, right? That process, here's what I'm getting at. That process can take place over years and decades and centuries, or it can take place over weeks or even days, or perhaps even hours. That's the thing I'm getting at here, see? We talk about Lake Missoula, and you get this picture of the standing body of water there. Oh, well, it was there for 50 years, and then, it was slowly rising. Maybe after 100 years, it finally got high enough that it was overcame the resistance of the glacial ice dam, burst out, flowed out, the lake emptied, the glaciers moved back, sealed off the valley, the water began to slowly rise again over decades, and after 50 or 100 years, the process repeated. What I'm suggesting is that glacial Lake Missoula may have filled in a matter of just days. You see, Lake Agassiz may have been formed in a geological instant. It may not have been something that was there in any given static form for centuries or centuries. It may have been a short-lived, and see, here's the point. Even though it's short-lived, all of these things that it's creating, all the erosional and depositional features are going to be similar. The main difference, of course, is that if you have a catastrophic flood, you're going to have much coarser material that is being transported. Now, here's the thing. Glacial Lake Missoula, okay, so if you go to the furthest reaches of that lake, which are several hundred miles removed from the outlet where the ice dam would have been, and not only removed just by distance, but removed because the route from the distal reservoirs to the outlet point is very convoluted. So if you've got a reservoir that's draining, if you got a single reservoir like a bathtub and it's got one outlet and you open that outlet, everything's going to kind of drain uniformly out of there, right? As soon as you open the outlet, the first pressures are going to be when the water's the deepest. As the water goes down, the pressure declines, the volume of water will decline correspondingly until finally you get down and the last bit of water is going to drain out as a trickle. You got that picture? Okay, now you look at Lake Missoula and you go to the distal reservoirs would be, for example, the Bitterroot Valley, where you can go down and you're a couple of hundred miles distant, not only by the route to the river, but many bends and turns and even hairpins. Now, bear in mind that every time a flow of water has to reverse direction and go around, say, a hairpin turn, what's it doing? It's losing momentum. So it's going to take, just like, even though you remove the outlet where the ice dam is, and then the initial rush of water is out, in the distal reservoirs, it's going down, right? And so the final draining should be a very gradual affair, and the sediment that's left behind should be of a very finer nature that's proportional to this slow final draining of the water. And if you had multiple Lakes Missoula forming, as the current models say, 40 to 90 Lake Missoulas, there should be very precise evidence, sedimentary and stratigraphic evidence of each one of these lakes in those most distal reservoirs where the energies involved in the draining were very low energy. But when you go in there, you don't find normal lake varves. What you find, and then we will, in upcoming episodes, we'll be showing you pictures. Brad and I have visited a number of rock quarries and gravel quarries, and what you find is massive thick layers of broken rock, very little soil. There's some soil, maybe 10,000, 12,000 years of soil on top. But under that, it's all masses of broken rock that has the appearance of direct deposition from turbulent suspension. And you don't see what I just described, which would be something you should normally see in a typical lake per se. So there's a lot of questions about this. So when you say, going back to Lake Agassiz, there's no doubt that there was water there in tremendous volumes. There's no doubt that the water was there over prolonged periods of time because, remember, the whole deglaciation process took 5,000 or 6,000 years. But within that framework of time, it seems that there were periods of highly accelerated pulsed melting, right? Glacial Agassiz could very well have been the result of one of these episodes of pulsed melting because, as we're going to be finding out as we're looking in further at this geomorphic, this grand array of geomorphic evidence, is that all over the ice sheet, this vast 6 to 7 million square mile area of ice sheet, there were a whole series of tremendous melting events that occurred. You almost could picture somebody just bombarding the ice sheet with nuclear bombs and creating these tremendous zones of concentrated melting. And really, when you look at the melting pattern, that's what you see. You don't see a continuous marginal retreat like one would expect as we look at the retreat of, say, for example, the Little Ice Age glaciers that we've talked about so frequently. That ain't what we see. We do see marginal melting, of course, but juxtaposed upon that is something else. And that is that you have these epicenters of intense melting. And so when we're looking at these, again, it gets us back to this idea of the dominoes that we were talking about. Well, you could say, okay, Lake Hind was fed by Lake Regina, and Lake Regina was fed by Lake whatever, which might have been, okay, so you got this cascading effect. So Regina overflows into Lake Hind overflows into Lake Souris, then Lake Souris overflows and creates the Souris spillway that eventually, ultimately flows into the Missouri Valley, right? But here's my question. If you describe it as a domino effect, and you've got a series of dominoes stacked up, right? Everybody knows, everybody's seen, you push one down and they all go down. But what caused that initial impulse? What started that first domino? That's the question I'm raising. That's the question that I want to get to, because I think that's the crux of the matter. When you say Lake Missoula, okay, fine. Over 600 cubic miles of water filling mountain valleys right up almost to the divides in some cases, where the area, the net area of the lake itself far exceeds the area of the entire catchment basin, right? Where the hell did that water come from? Answer me that. Where did that water come from? Is it meltwater? That's a hell of a lot of meltwater. Well, if it's meltwater and we're thinking normal glacial melting, that's marginal melting. So if the margins are melting to feed all of this water into glacial Lake Missoula, that means they're retreating. How can they simultaneously be retreating, providing the meltwater, but at the same time providing a perfectly stable, 100% stable glacial ice dam up to pressures in excess of 950 pounds per square inch at the glacial heel? I think that's a fair question to ask. And I don't see anybody really asking that and going, something ain't right here. See, what we need to be looking at now is this comprehensive picture of the whole deglaciation process, which was catastrophic, unimaginably catastrophic, and apparently happened in, like, perhaps, and I think this is what's the likely scenario, 3 great waves of catastrophe, 3 great pulses of catastrophic meltdown to get from a world enshrouded with 6 million to 7 million cubic miles of glacial ice piled up, twice the volume of glacial ice that's on the Earth today. How do you get from that to the world we're in now in a matter of a few thousand years? How do you get rid of that? If I said to you, Mike, Russ, Kyle, Brad, come up with a scenario so we can utterly eliminate all of the ice on the South Pole, how would you do it? Well, that's how complex this problem is, because the energies required to get rid of that ice would be equivalent. Because if we go back 15,000 years ago, Hudson Bay was the center of an ice mass that's the size of the South Polar ice mass. It was up to 2 miles thick. Okay, how do we get from that world to this world? How do you get rid of that ice? Where do you get the energy to convert that ice into meltwater and do it in a way that looks like the damn thing was just assaulted by, 100 or a couple of hundred hydrogen bombs that create epicenter meltings? It's interesting. I don't have the answer, but we're working on it. And this brings us to drumlins and the work of John Shaw, because we are going to be getting really into the work of the late John Shaw, and we're going to be privileged in an upcoming episode to be joined by Jerome Lessman, who was one of the co-authors of John Shaw's last paper published posthumously. So we're going to look into that, because what John Shaw did was he came up with what I think is the only plausible explanation for the origins of drumlins. What are drumlins? Kyle, I'm calling on you, my friend. Find us, look up drumlins.
I think they're well, can I give what I think they are?
A layperson's vernacular version?
Yeah.
Sure, go ahead.
I think that they are streamlined erosional residuals that are subglacial, from subglacial flows, perhaps.
Close.
And they could be depositional.
They're distinct from streamlined erosion residuals. The distinctions are the result of their environment of creation, because the streamlined erosional residuals that we are seeing are formed by flowing water with a free surface. Drumlins are formed by flowing water that's under pressure, that has a lid of glacial ice. So that, in other words, if you have a flow of water with a free surface, that means it's free to oscillate between depths, right? When you have subglacial flows, it can't do that. So the water is moving under pressure. And what it does is it begins selectively shaping the substrate, which in most cases, because it's under ice, is going to be thick layers of glacial till. So what it does is it begins to differentiate. You might have some larger boulders here, or, the glacial till is not going to be perfectly uniformly distributed under the ice sheet. There's going to be places where it's thicker, some where it's thinner, some where it's coarser, some where it's finer. There may be some large boulders or naturally occurring outcrops that affect the movement of both ice and water. But the point is that the water then begins to selectively shape these masses of glacial till, which are forming obstructions. The glacial till is going, oh, hold on. We're, there's all of this hummocky stuff and rocks and boulders and gravel. The water's trying to come over it. It's providing resistance, but the water's going, no, screw you. We're coming through. You're trying to obstruct us, all of us water streams from flowing through. No, we're going to actually reshape you so that you can provide less resistance. And that's what it does. It begins to reshape the layers of glacial till into these streamlined, almost inverted boat hull forms, right? Yeah. So what we're going to do is I'm going to take a second here, and we are going to look at a few pictures of drumlins just to get the idea. This is the so-called Livingstone Lake drumlin field. Notice the arrow, flow direction. Now, the theory is that these inverted boat hull shapes, these elongated, streamlined forms, were formed by highly pressurized floods beneath a cap of glacial ice. And because of that, with these additional pressures exerted on the substrate by the flowing water, it was able to more effectively shape and mold them into these forms. So this is a drumlin field, a drumlin swarm. Now, we'll look at some more here to get an idea. This is just a Google Earth image. What we need in one of our projects, that once we get a few more resources at our disposal, one of our projects is going to be extensive LiDAR analysis of the drumlin fields. One of the problems when you try to analyze drumlins from the ground is that, particularly because some of these huge drumlin fields in Canada, in Wisconsin, in New York, and so on, are covered by forests or canopies of vegetation, which makes it difficult to see them. So LiDAR now will provide the ability to penetrate the forest. Like when we've been in Canada looking at drumlin fields, oftentimes if you're on the ground, you don't really know that you can't see through the forest that, yeah, right next to you is a nice, beautiful, elongated, streamlined drumlin. This will give you an idea of the scale of a typical drumlin. And there, you see how it's forested. Now, typically in drumlins, you've got, go back to here, the blunt end is the up current, the tapered end is down current. So again, drumlins are a paleo current indicator. There are some exceptions to that, but typically drumlins follow that particular geomorphic pattern. Blunt on the upper end and tapered on the down, or the, yeah, so I'll say this, blunt on the Stoss end, tapered on the Lee end.
And are they mostly the same height, like elevation?
They can be very big, like you see, this is a big drumlin. This is probably a couple of miles long. And then notice, you can see actually there's another profile of a drumlin right here. You see, can you see the other drumlin hill right here?
Yeah, I see it.
Yep. And then if you look out here, there are other drumlins. They're harder to see, but they're out there. This is, so you're looking actually at a drumlin swarm here. So one of the things that we did, Brad and I did in 2016 with Jerome Lessman, when we spent 4 days out in the field with him, was we went to some of these drumlin fields up in BC, in British Columbia, up on the plateau country. And one of the things he was looking was for these scour marks on these Stoss or upper ends, because those scour marks, and we'll explain why, and when he's on, we'll get into an extensive discussion of that, why these are so critical for demonstrating that these were actually produced fluvially, and not, as most theories would invoke, is that there's some indefined way that the glaciers themselves grinding over the substrate of till somehow shapes them into these elegant streamlined forms. Whereas Shaw came along and said, no, it's the water flowing under the glaciers. But Shaw's, for the most part, ideas were considered very controversial and actually tended to be rejected. And why do you suppose that would be, Kyle?
Because it suggests some other type of source for the floodwaters that they didn't want to accept.
Indirectly, yes, but
okay.
It's the scale.
Okay.
Just like with Brett's, the scale of the scabland erosions in eastern Washington is of such a scale, and the floods required to produce that complex of mega scale erosional forms was such that Brett's couldn't really explain the ultimate source of the water, not back in the 1920s or 30s. That was why when, Glacial Lake Missoula, there we go, glacial lakes. We've seen glacial lakes here in modern times. They fill up behind an ice dam. They break through the ice dam. They flow out in these outburst floods, or Icelandic term Jökulhlaups, and all we got to do is scale up 2 or 3 orders of magnitude to explain Brett's channel scabland, right? But what they ultimately said was, early on, was that, well, you cannot provide a source for the volume of water required for your floods. Therefore, the floods didn't happen. What we now see is the critics of John Shaw saying, well, if you're right that these drumlin forms were formed by subglacial floods, well, the scale of these drumlin fields is so vast that the amount of water necessary would be almost inconceivable. Well, therefore, they weren't produced by subglacial floods.
Yeah, and the source wouldn't be an outburst flood. It would be subglacial. So,
well, yeah, it's subglacial. Now, here's the thing. A subglacial flood is ultimately going to be an outburst flood, because at some point it is going to exit the glacier. And that's what we see. We're going to come back and we're going to take a closer look at the Finger Lakes in western New York as a beautiful example of what happens when you've got this huge rush of water coming subglacially, and what happens when it bursts out at the glacier margin. We'll also look at comparable examples out in eastern Washington, where you see water gushing beneath the Okanagan lobe, and what happens when it finally bursts free.